Hello and welcome to our SDC21 presentation, CSI Driver Design, bringing a parallel file system to containerized workloads. My name's Eric Weber. I'm a software engineer at NetApp and one of the primary contributors to the brand new BGFS CSI Driver project.
And I'm Joe McCormick, also a software engineer contributing to the CSI Driver and other Kubernetes-related initiatives at NetApp.
So for the past few years, Joe and I's primary responsibilities have been around enabling our customers to use high-performance parallel file systems backed by NetApp E-Series storage. And over the last year, that's evolved into the design and implementation of a container storage interface driver that allows customers to mount a BGFS parallel file system to a Kubernetes or other container orchestrated workload. With SDC21 coming up, we thought it'd be a good opportunity for us to kind of compile down a lot of the design decisions that we've made over the past year in the hopes of helping people who are just starting out on their CSI journey kind of understand what decisions need to be made with the context of how we made those decisions. And in addition, if you've already kind of been on the journey for a while, we hope that our perspectives on how we solve some of the same problems that you've solved will be helpful as well. Now, if you're brand new to CSI and don't know what it is, I'm going to spend just a couple of minutes talking about it. So CSI stands for Container Storage Interface. And I'll start with the assumption that containers need access to external storage. Now, that might be pre-provisioned storage that's kind of outside of the container orchestration environment, or it might be dynamic storage that's created at the exact same moment that a container is created, but they need access to that storage. At least in Kubernetes, this has actually been built in for a long time. So in the old system, a storage vendor like NetApp could create a plugin that would allow Kubernetes containers to mount some type of external storage, but they'd have to contribute the code for that plugin to Kubernetes itself. And that meant that it was kind of tied to the Kubernetes release cycle, and also it made the Kubernetes maintainers, the community, kind of responsible for the code that was produced. This doesn't scale really well with Kubernetes getting really large and with many storage providers wanting to integrate. So the new, better way of doing things is container storage interface. And the idea is that CSI is a specification that allows a vendor like NetApp to write a standalone, fully featured plugin. And when I say fully featured, I mean it can handle pre-provision volumes as well as dynamic provision volumes, but even extended features like snapshots, cloning, expansion, etc. And a vendor can write a single plugin that works with Kubernetes, but it also works with Nomad or Mesos or Cloud Foundry or any other orchestrator that follows the CSI spec. Now, when I say spec, what I'm talking about is a protocol buffers specification file or a Proto3 specification file. This defines a set of RPCs that a vendor needs to implement in what is essentially a gRPC server. So the container orchestrator control plane can make RPC calls to the plugin, and then the plugin can go out to external storage and make things happen. When I talk about a plugin, there's really kind of two aspects that I'm talking about. There's the controller service aspect, and that's responsible for the dynamic creation and deletion or provisioning and deprovisioning of storage. And then there's the node service aspect, which is responsible for mounting storage to a node and then mounting that same storage into a container namespace. And this separation of concerns is really nice because it allows the container orchestrator maintainers to just worry about when and how to make RPC calls to a plugin. And it allows the vendor to write a plugin that's primarily concerned with communicating to the external storage platform that they already know how to support.
Well, the intention of this session is not to describe BGFS in depth. A high-level understanding of the architecture is helpful to relate to the various challenges and design decisions involved in developing a CSI driver for BGFS. BGFS is a parallel file system, similar in many regards to the more well-known Lustre. In general, parallel file systems are designed for workloads requiring high-performance, often sequential access to very large files. They typically do so by storing metadata describing the file and directory layout and attributes of each file separately from the actual file contents. Metadata servers are only involved in file open and close operations, and metadata is distributed on a per directory basis to help avoid metadata nodes from becoming a bottleneck. The file contents are in turn striped across one or more storage nodes that, in the case of BGFS, store the data in one or more storage targets that are typically a block device presented from a local or remote storage system. This architecture helps ensure no one piece of hardware becomes the bottleneck when tens, hundreds, or even thousands of clients need to access the same file. This is a notable difference between parallel scale-out file systems like BGFS and other distributed scale-out file systems. In the latter, the file system may span multiple physical storage nodes, but each file still resides on drives owned by a single node. In other words, you cannot scale throughput to a single file simply by adding additional nodes. With BGFS, the number of storage targets, the amount of data written to each target, and even the specific target can all be configured on a per file or per directory basis. This allows optimization of the file system for different workload profiles and is a good example of the type of unique requirements a parallel file system brings that we need our CSI driver to expose to the end user. Nodes wishing to access the Bgfs file system, for example, a Kubernetes worker node, simply install the Bgfs client, which provides a kernel module to mount the file system. BGFS also provides a utilities package that includes the Bgfs CTL command line tool used to manage the file system and apply any dynamic configuration that doesn't require restarting Bgfs services, notably the aforementioned stripe patterns. There's also a Bgfs management service that serves as a registry and watchdog for all of the nodes in the file system, and the only required configuration for a Bgfs storage, metadata, or client node is the IP or hostname of the management service for the file system it wishes to participate in. This is notable for later when we need to tell a container orchestrator how to access a particular Bgfs file system. Today, we're going to take you through 6 key design decisions we had to make as we developed a CSI driver for BGFS. The concept of a volume is a fundamental part of the CSI specification and defined as a unit of storage that will be made available inside of a container orchestrator managed container via the CSI. BGFS largely provides POSIX file system semantics, which raises the question, what is a volume in the context of BGFS? The only analog is a directory, but directories don't naturally provide the capacity constraints and isolation implied with the traditional definition of a storage volume. Therefore, within reason, it is up to our driver to provide the expected characteristics of a volume using directories in BGFS. Capacity was the first area where we invested quite a bit of time thinking about how it could and should work. BGFS does provide quota tracking and enforcement based on Linux users and groups, and we briefly considered creating each directory representing a volume with a unique group and setting the setGID bit so all new subdirectories and files would inherit that group, thus allowing us to configure a group quota based on the requested capacity. While this would not be overly complicated to implement, we felt practical usage was difficult and left much to be desired. For one, to avoid conflicting with existing groups, administrators would have to provide us with one or more GID ranges we could use when provisioning volumes. And while we could enforce the capacity, there was no way to guarantee the users the full capacity they requested. This approach also required administrators to restrict what user and group containers can run with to avoid a root user being able to change the group, thus breaking the quota enforcement. For those and other reasons, we felt that currently BGFS does not provide a good way to restrict the capacity consumed by a single directory, and any work we do now would likely conflict with future BGFS enhancements, creating something that would be unwieldy to maintain long-term. For now, BGFS volumes in Kubernetes are essentially thin provisioned. The capacity requested has no bearing whatsoever, and users are free to create volumes that individually or in aggregate exceed the capacity of the BGFS file system. This allows administrators to separately monitor available capacity based on actual user consumption and add capacity behind the scenes without users being the wiser. For more on how the driver handles capacity, check out our documentation on GitHub. Luckily, isolation proved much simpler to achieve. For each directory representing a volume in Kubernetes, we create a bind mount that is ultimately what is exposed inside the container, thus preventing a container from ever breaking out of the intended directory or even knowing where in the BGFS file system the directory representing its volume request is located. Of course, this is a simplistic view of how this works under the hood. If you want a full view, when we have a container orchestrator involved, BGFS is first mounted to a staging target path that is used to create the bind mount to a target path that is ultimately what the CO makes accessible inside the container, inside the container's mount namespace at the mount path specified by the user. The staging and target paths are provided by the CO, and in the case of Kubernetes can be found under the var-lib kubelet directory. With clarity on the definition of a volume, the next decision we had to make was if we wanted to support dynamic provisioning. A very basic CSI driver could just take an existing volume, a directory in our case, and make it accessible to one or more CO managed containers. This is helpful if the BGFS parallel file system contains datasets at well-known locations that need to be accessed by containerized applications. However, a common use case for parallel file systems is scratch space. In other words, the ability for applications to request some arbitrary amount of storage for the duration of a job without necessarily caring about where that storage is, and likely only a subset of any data written to the location needing to persist beyond the job's duration. So it was clear from the outset the ability to dynamically provision volumes was desirable for the BeeGFS CSI driver. The CSI spec allows for dynamic provisioning if a driver advertises the create delete volume capability and implements the controller plugin. This plugin is essentially a gRPC endpoint that serves CSI RPCs and needs to be able to run anywhere, not necessarily on the node running the containers that actually consume the volumes. This is notable in the case of BeeGFS because it does not have a REST API enabling the programmatic out-of-band management found in many storage systems to perform tasks like creating a volume or presenting it to a host. Earlier, I mentioned BeeGFS provides a utilities package, including a BeeGFS CTL tool used to manage the file system. This does provide us the ability to create directories in a BeeGFS file system without actually mounting it and running makedir. But more importantly, it lets us create directories with BeeGFS-specific options like stripe patterns, which is something we'd like users to be able to specify when requesting a new volume. However, it does not have the ability to remove directories from the file system, which is required by the specification to fully implement dynamic provisioning. So ultimately, our controller plugin does two things. When the create volume RPC is called, we use BeeGFS CTL to create a new directory configured with those provided BeeGFS-specific parameters. More on that when we talk about how the driver handles configuration, but for now, know that striping and permissions are passed in the create volume parameters map. Then when the delete volume RPC is called, we mount the BeeGFS file system to perform the Go equivalent of an RM-RF for the directory representing the volume. While our driver already requires administrators to install the Bgs client and utilities package on any node that may use Bgs volumes, our implementation of delete volume does have the disadvantage of extending that requirement to any nodes that need to run the controller plugin, which was something we hope to avoid. However, this hasn't generally proven to be an issue, except in the case of container orchestrators with nodes that are incapable of mounting a Bgs file system. For example, Windows, which doesn't currently support BGFS, or potentially operating systems like Red Hat CoreOS, which deliver updates to the OS as an atomic unit, and installing new packages or adding additional kernel modules is not as easy as firing up your favorite package manager. In practice, it is easy enough for administrators to configure the controller plugin and other components of our CSI driver to only run on certain nodes of their cluster. Future work is also planned around how we integrate the CSI specs topology support into the driver, simplifying use in environments where, say, only a subset of Kubernetes nodes are dedicated for HPC or other applications that need to use BGFS.
So if you read the CSI specification, you'll find a number of optional RPCs, and some of them are related to kind of extended features like cloning, volume expansion, snapshots, etc. But some of them are in the typical create, mount, delete path that you would expect pretty much every CSI driver to support. A couple of the RPCs that I want to highlight here are controller publish volume and node stage volume. So controller publish volume is an RPC that goes to the controller service, and it gives it an opportunity to reach out to the control plane of some external storage provider and do something that would allow a volume on that storage provider to be ready to be mounted to a node that's soon going to be running a workload. And the other one is node stage volume, and this is a node service RPC that allows the node service to pre-stage a volume at a particular global location on a node before, again, remounting or bind mounting that volume into a container namespace. Now, if you look at the spec, you'll see a number of different diagrams that are very similar to the diagram that you see here. Depending on the needs of your particular storage provider, you'll use one of these life cycles. So a life cycle that includes all of the optional RPCs that I mentioned looks something like this. And I'll use the example of a block storage array like a NetApp E-series array to kind of give an idea of when these RPCs would be called and what they would do. So create volume might reach out to the array and provision a brand new LUN on the array. Before controller publish volume would do LUN masking. So it would reach out to the array and make sure that the volume was available on a particular node in the cluster. And then node stage volume might be an opportunity for the node service to do things like discovery, handle multipathing, and mount a file system from one of the partitions of a block device onto the node itself before node publish volume bind mounted that volume into the actual container namespace. Now, there was a lot of things that we had to think about in terms of BGFS when we were considering whether to implement these RPCs. For one, BGFS is a parallel file system. It's designed for parallel access. So there's no real reason that one node should be able to read and write to a particular file system while another node can't. All nodes can read and write from the file system at all times. And so we decided that we really didn't need to implement the controller publish volume RPC call at all. On the other hand, something that Joe mentioned was really important, right? A volume for us in BGFS CSI driver is a single directory. And you can't mount a single directory to a node. You have to mount the entire file system to the node. So we decided to use node stage volume as an opportunity to mount a whole BGFS file system to a node before using node publish volume to bind mount that individual directory. I will mention here that we thought about streamlining this maybe even a little bit further and ensuring that a single BGFS file system, no matter how many directories and volumes it contained, would only be mounted to a node one time before a series of node publish volume calls bind mounted all of its directories out. But we decided against that. And the reason is that for BGFS, different workloads might need to mount a BGFS parallel file system with different parameters. And we wanted every single volume to have the opportunity to specify how the file system should be mounted. So this is the volume lifecycle that we actually went with. Create volume, as Joe mentioned, it creates a directory on an existing BGFS file system. And then node stage volume mounts that entire BGFS file system to a location on the node at staging target path, which is something that the CO, the container orchestrator, provides us. Then node publish volume takes an individual directory representing our actual volume and bind mounts it into the container namespace. Something else that we had to consider, although at the beginning of the project, maybe we didn't understand how much we'd have to consider it, is how do you actually package the driver up for distribution? Essentially, the driver is just a binary that implements a gRPC server. You could deploy it to the nodes in your cluster in almost any way that you wanted, and you could use something like a systemd unit file to make sure that it was constantly running and constantly listening to the correct socket. But if you read the specification, what you'll find is that plugin packages should use a well-documented container image format like Docker for distribution. And if you read between the lines, you find that really the intention is that you will deliver the driver to your cluster using the same container orchestrator that it's supposed to serve. So if you want the driver so that you can enable Kubernetes workloads, you should deliver the driver using Kubernetes. And in fact, the Kubernetes CSI developer documentation spells out really only one officially supported way of deploying a CSI driver. And the idea is that you take the controller service and you package it up into a container and you deploy it to a single node, either using a deployment or a stateful set. And you take the node service, you package it up into a container and you deploy it to all nodes or some subset of nodes using a daemon set. And along with the container that has the driver in it, you also deploy sidecar containers written by the Kubernetes CSI community. And the reason for these sidecars is that your driver doesn't have any idea how to communicate with the Kubernetes API. It only responds to gRPC commands. So the sidecar containers communicate with the API server and then deliver RPCs to the plugin whenever is required. So we knew that we needed to package our driver up into a container, but for BGFS, there are a lot of implications around that. First of all, the BGFS client packages aren't available by default in any industry standard Linux distributions. And the BGFS client and some of the RDMA packages that we required as well, they're kernel modules. And there's really no good standard way of distributing kernel modules to a node through a container. It can be done, but typically a container contains user space processes. Even if we could distribute the BGFS client, the BGFS client license doesn't clearly allow us to do that. Now, NetApp and ThinkPark, who maintain BGFS, are really close. We have a good relationship. So it's probable that we could have worked something out. But generally, When we're distributing a new application, we typically try to reduce the amount of things that we have to distribute, right? There are security concerns when you distribute more and more things that would have to be very careful to make sure we take care of, and also licensing concerns. And so we kind of wanted to keep the distribution as small as possible. Now, a typical CSI driver mount operation looks something like what you see here. You have the node service, which is running in a container, and the container image that it's based off of has a number of libraries that are in it. For example, if your driver is built into an Alpine container, you'll have the mount user space administration tool. So your driver can call that tool, and that tool can make a system call down to kernel space to actually mount some external storage to the node. There are some things to be aware of here, though. First of all, a container can't make that system call unless it has the sysadmin capability. So you'll see every deployment manifest for every CSI driver giving the driver that capability. And it also only works if the kernel already knows how to mount that particular type of external storage, which of course is a problem for BGFS. Another thing that's needed is bidirectional mount propagation. I'll kind of smooth over that here for now, but I'll suffice it to say that the node service application needs to have a similar view to what's mounted to the node as the node itself does. And that's where the bidirectional mount propagation comes in. Now for BGFS, that whole aspect, the node service application and the mounting aspect, wasn't much of a problem. It's really in the controller service application that we have more of a challenge. As Joe mentioned, there is no REST API for BGFS, so we need to use this BGFS CTL command line tool to be able to do things like stripe our new volume over the right storage targets. And for all the reasons that I mentioned, we didn't want to include the BGFS CTL tool within the container that we distribute to our users. And so the way that we got around this was actually by mounting the host root file system to the container read-only, and then chrooting to that file system and executing the host's own version of BGFS CTL whenever we needed to. And we're actually not the only driver that does this. This is a pretty common trick that a lot of CSI drivers do. If you look at the way that they're implemented, CSI drivers will use the host's own iSCSI ADM tools, its own multipathing tools, even its own mount utility can be used if you're willing to kind of take advantage of this possibility. And that allows you to ship a really small container, maybe even based on a distroless image if you can use the node's own resources. Of course, the disadvantage here is that you have to give the driver container quite a few privileges in order to make this work. And so we really shift away from the container being a good way to isolate the driver application and shift more towards the containers a really convenient way of distributing this application that still needs a large number of privileges.
The next area we're going to look at is how we expose Bgfs configuration through the driver. There are two types of configuration we needed the driver to handle. First, we had the Bgs Client Configuration. Each Bgfs mount point requires its own configuration file, if only to set a unique UDP port. This does mean each Bgfs volume we create will require its own configuration file. And this file also contains a number of other parameters, mostly things an administrator may want to change based on the unique constraints of the underlying hardware. For example, if RDMA is in use, what interfaces to use for Bgfs traffic, along with other typical settings like retries and timeouts. Once you have this file set up, changes are not expected regularly and would require remounting Bgfs to take effect. The second type of configuration is anything we can apply dynamically using Bgfs CTL without restarting services or remounting. This configuration would be more interesting to an end user, as it allows them to directly influence and improve their container storage performance using Bgfs storage pools and stripe patterns. One challenge is providing a simple enough way to expose these knobs to the end user, as they may not necessarily be a storage expert. So let's talk about what the CSI spec provides regarding configuration. When we create a volume through the dynamic provisioning workflow, the CO can provide us a map of parameters. For Kubernetes administrators, typically create storage classes that describe what on-demand storage is available in the environment. So this seems like an obvious place to carry all the configuration needed to provision a volume, including both the Bgs client config file and any dynamic configuration. However, while the node stage volume and node publish volume RPCs accept the volume context returned by the initial create volume, the corresponding unpublish, unstage, and delete volume RPCs do not. And we've already established in order to delete BGFS volumes, we have to remount the file system, which requires recreating the Bgfs Client Configuration file. Furthermore, the spec indicates the volume ID alone should be enough to identify a volume. In other words, we can't really rely on being provided the same parameters by the CO after initially creating the volume. One obvious option is for our driver to keep track of all the volumes that were created, so we could persist the original context they were created with. But we were very hesitant to introduce the requirement for our driver to maintain its own state unless unavoidable. Technically, all we need to uniquely identify a volume in BGFS is the management service IP or hostname and path to the directory in BGFS representing the volume. This combination is enough to create a meaningful volume ID, and after further thought, inextricably tying the Bgfs client configuration to each volume may not be desirable. For example, not all Kubernetes nodes may have the same hardware topology, so there could be a need to configure different preferred interfaces for BGFS connectivity when a volume is mounted to different servers. However, it does make sense to have dynamic configuration like permissions or stripe patterns apply to individual volumes, or at least volumes created from a specific storage class. So the driver relies on two sources for determining how to create and mount BGFS volumes. All client configuration is handled through a config file, which is managed as a config map when deploying to Kubernetes. The driver starts with the default etc Bgfs Client config file provided when installing the Bgfs client package to the CO node, then applies any user-specified values in its own config file over the defaults. Not shipping the driver with a full copy of this file means any changes to the defaults in future releases are immediately reflected by simply upgrading the client package. It also means we can support most added or deprecated parameters with no changes to the driver. Thus, one viable approach would have been to have administrators update the default config file at etc Bgfs, and we could forego performing any additional Bgfs configuration using the driver. However, we felt this could prove burdensome to manage, especially when dealing with large Kubernetes clusters, multiple Bgs file systems, or if the individual responsible for managing the configuration does not have easy access to the Kubernetes nodes. Another consideration is, while today there is still the prerequisite to install the Bgfs client, long-term we want to manage the lifecycle of the client install using the driver, so configuration management is something we anticipated having to solve sooner or later. Thus, right off in the 1.0 release, we allow administrators to manage all Bgfs client configuration using the driver. You can define configuration that applies to all file systems and nodes, specific file systems, specific nodes, or even a specific file system mounted to a specific node in that order of precedence. This gives administrators complete flexibility to configure the CO nodes for BGFS, regardless if their cluster is comprised of a diverse mix of hardware. Then we rely on the CO to provide us any dynamic configuration specific to a particular volume as part of the create volume request. Today, that includes stripe patterns and permissions. These are applied using BGFS create dir, and there's no need for us to persist these details as they're always available by simply inspecting the directory in BGFS. Thus, we consider our volume ID to be a uniform resource identifier, or URI, composed of the BGFS management hostname or IP and the path to the directory representing a particular volume. To understand common or best practices in developing a CSI driver, we've looked at a number of other drivers and noted this URI approach is not uncommon. Combining this URI with our startup configuration allows us to perform all steps in the volume lifecycle, including unmounting and unstaging the volume from one node, staging and mounting it to another, and deleting it when it is no longer needed. Over the next few slides, we'll look closer at how we implemented handling Bgfs client and dynamic configuration. This slide summarizes the different sources used to build the Bgfs client configuration file for each volume's mount point. The Bgfs management IP is just injected based on the URI of the Bgfs volume we're handling a mount request for. And each Bgfs mount point needs its own UDP port, so we implemented a function to handle identifying and assigning an available ephemeral port. One quirk of Bgfs is some of the parameters in the Bgfs client config file require you to specify a path to a separate text file. For example, to prioritize and restrict what interfaces Bgfs uses, you create a file listing out the interfaces and specify the path to that file in the Bgfs client config file. Our configuration file is written in YAML, so users simply provide a list for those parameters, and we handle creating the necessary files in the right location and referencing them in the actual Bgfs INI config file. Handled in this very similar way, Bgfs also supports shared secrets for connection-based authentication. While the best way to handle data we want to avoid exposing in plain text varies by the CO, we start by requiring users to provide a separate file listing out the secrets for each file system the driver needs to interact with. Then, at least in Kubernetes, this is stored as a secret, which provides some measure of protection to avoid logging or leaking data that may be sensitive. All other supported key value pairs, for example, the option to enable RDMA, are specified in the YAML equivalent of a Python dictionary. Well, again, CSI is meant to be CO agnostic. Everything on the slide will be specific to Kubernetes, largely because it's the only CO officially supported by our driver, so we've had minimal exposure to the way other COs implement dynamic provisioning. For a lot of this to make sense, though, you'll need a 30-second introduction to storage in Kubernetes. First, containers in Kubernetes are actually deployed as pods containing one or more containers that share access to the same networking and storage resources. Storage classes describe the various storage options available in the cluster that can be requested on demand. A persistent volume, or PV, is a piece of storage in the cluster that has been statically provisioned by an administrator or dynamically provisioned using a storage class. A persistent volume claim, or PVC, represents the actual request for storage by the user. So when a user requests storage on demand for their pod, they submit a persistent volume claim against whatever storage class suits their need. A key benefit of container orchestrators like Kubernetes is they abstract away underlying compute, storage, and networking infrastructure away from end users, often developers who just want to focus on whatever application they're responsible for building. And when it comes to storage in Kubernetes, storage classes are a fundamental way of doing this. There are two required BGFS storage class parameters. The first is the management IP for the BGFS file system. If you have multiple BGFS file systems you want to make accessible to Kubernetes users, you could do so with multiple storage classes. The second is the path to a directory in the file system where you want us to create subdirectories representing the BGFS volumes created from the storage class. If this path doesn't exist, we will take care of creating it. And then we have a number of optional parameters that adjust how we create the directories representing the BGFS volumes. Well, BGFS has lots of knobs to optimize for various workloads. As I said before, one challenge is providing a simple way to expose these knobs to the end user who may not necessarily be a storage expert. We initially considered exposing these knobs to users as options when they submit a persistent volume claim, but ultimately decided this did a poor job of fitting BGFS into Kubernetes paradigms around storage. So instead, we expose them to the administrator by allowing them to be configured on storage classes. The thought is the administrator is better equipped to understand the storage needs of their users and create meaningful storage offerings that fit the unique needs of their organization. This also means instead of having to remember which combination of BGFS parameters work best for each workload and set them on every persistent volume claim, users simply query for the available storage classes in the cluster and choose the one that best suits their current need. Of course, advanced users could always work with their Kubernetes administrator to develop a custom storage offering. In other words, create a storage class optimized for their particular use case. Before we walk through these examples, it's important to note that the striping and storage pool configuration set on a directory in BGFS using BGFS CTL is inherited by any new files or subdirectories unless manually overridden. So when we set these on a directory representing a BGFS volume, any user files or subdirectories will inherit this configuration. Let's say an administrator has created two BGFS storage pools, one grouping all their SSD-backed targets, and a second with their nearline SaaS targets. Then they can set up a series of storage classes that map back to these storage pools and various combinations of chunk size and number of targets to optimize for different workload profiles. As a result, users don't have to concern themselves with understanding the semantics around how BGFS stores data, but can still take advantage of its features by simply choosing a storage class. In this example, an administrator has set up two storage classes optimized for fast access, one for small files and another for larger files. Then a third storage class that offers a balanced configuration for storing data that needs to be accessed infrequently. While the underlying parameters are BGFS specific, they are a good example of the type of unique storage configuration CSI developers need to take into consideration when thinking about the best way to expose storage knobs using their driver.
These first 5 decisions that we've discussed were really around design and could be handled before ever starting with any sort of implementation. But the last one that we want to discuss is implementation itself. How do you get started? So our team kind of looked at a good, better, best scenario for ways that we could begin the implementation of the driver. And the first and most obvious one was to start from the protocol buffers specification itself. So if you're not familiar, protocol buffers allows you to download the protocol buffers compiler and compile a specification with all of the RPCs and messages that is included. into any number of stubs in any number of languages. C++, C#, Python, Golang, Java are all supported, as well as others. So you'd start with something like what we see here on the top left, a series of basic RPCs, and you'd end up with a stub in the language of your choice. And so you might think, well, I've got a team of Java developers, so I'm going to start implementing the CSI driver in Java based on the stub that I get from the compiler. And you can do that, but I'll caution you that every CSI driver I've ever seen is implemented in Go. Kubernetes is implemented in Go, and most Kubernetes adjacent projects are implemented in Go. So if you do it in a different language, you're probably kind of throwing away a treasure trove of potential examples and an opportunity to see how other people are doing things. For our team, Go was the obvious choice because we already had some Go experience, but we actually found a better option than compiling the spec ourselves. The CSI spec maintainers actually have a pre-compiled version of the spec in both C++ and in Go. And so you can actually import that pre-compiled Go stub as a module into a new project. And that looks like what you see in the middle of the screen here. And so you have a bunch of different Go interfaces that you can implement, as well as the internal wiring for a gRPC server that you can get started. So one option would be import that as a module and then get started fresh on our CSI driver. But what that doesn't give you is things like, how should I lay out the project so that I can implement interfaces in a place that makes sense? How do I build the project, and how do I get it into a container, and how do I test it, and how do I deploy it to a container orchestrator? So for our team, as we were looking to the answers to these questions, we came across the host path example driver project. And this is a project that's maintained by the Kubernetes CSI community. And it's a fully fledged driver that you can download, and we did download. And what we essentially did was we found all of the host path related code, we gutted it, and we put in our own BGFS related code. Now, you may or may not like that approach. You might prefer to use the host path example driver as a kind of blueprint or outline and implement your own driver from scratch. But it's very clear to us, looking at the breadth of the CSI drivers that exist in the open source community, that almost everyone is taking this example driver and emulating it as they implement their own driver. And that's totally fine to do. A host path example driver is Apache v2 licensed. The Bgfs CSI driver is Apache v2 licensed. So as long as we're careful about giving attributions to the appropriate people in the appropriate places, it's a great way to get started with CSI driver implementation, and something that I highly recommend. Now, there are a lot of other design and implementation decisions that we've had to make over the last year as we've gotten started with the Bgfs CSI driver, and we can't possibly fit them all into a presentation and discuss them like we have. And so these next couple of slides are some additional decisions that we've put in the slides with some additional context around them, and we recommend that you take a look through them at your own convenience, and feel free to reach out to us, whether to ask us questions or to start a discussion about some of the extra things that you see here. If you do want to reach out to us, please do feel free to find us on our GitHub page for the Bgfs CSI driver and create an issue. You can email the team or either one of us individually, and you can look out and find a number of blogs that we've written, some of them more marketing in focus and a lot of them more technical in focus, for a little bit more of information on how we did things as we got going on this project. Please do feel free to rate this session. It really helps us understand whether what we're doing is valuable to you, and also what we can do to make it more valuable to you. But otherwise, on behalf of Joe, I want to thank you for attending this SDC21 presentation, and I look forward to hearing from you soon.